Why would we want to tame complex software? My name is Eric Normand, and I help people thrive with functional programming. So I'm writing this book, as you may know, and the title was chosen for me by my publisher. They work with a lot of books, a lot of titles, so they know what does well, and I didn't have a better idea than this, and they used a lot of elements from what I was thinking for a title. So the title is Taming Complex Software, a Friendly Guide to Functional Thinking. A couple episodes ago, I talked about what functional thinking meant and why I like the term. I didn't choose it, but I like it. It's grown on me since they chose it. And I want to talk about this idea of taming complex software and what that really means, what it has to do with functional programming. Why is that the title of the book? This was actually something I came up with early in our discussions, my discussion with the publisher. They do this really cool exercise, and they said, why don't you write down the super secret subtitle of the book? And it doesn't even have to make any sense. It doesn't have to be coherent. It doesn't have to be catchy. But just write down the subtitle of the book and the title, the title and subtitle. And so I came up with Taming Software Complexity as one of the phrases. And so they kind of, chewed on that for a while. They liked it, but they changed it to Taming Complex Software. I think that there was some issue with complexity being, complexity theory, and I was not going to go there in the book, and so they turned it into Taming Complex Software. But I still like Taming Complex Software. It probably makes more sense, even though I think of myself as going directly at the complexity. I think that I am operating on the software, and the software is what's getting tamed. So it makes a lot of sense. But why complexity at all? Why are we talking about this complex software? And that's what I want to go into in this episode. So, software complexity is the reason why software gets harder to write as it gets bigger. As you add lines of code, the complexity goes up much faster than linearly. And so every language, every paradigm has this curve of scale that it can reach. Now, this is also true in other systems, right? If you can only communicate with handwritten notes because you don't have a printing press yet, the size of your kingdom can only get so big, right? You can only, rule and organize and work with a kingdom of a certain size, right? And so a lot of energy is put into systems of communication, systems of record keeping. All these things help manage the complexity of a bigger and bigger kingdom, right? As your kingdom gets bigger, it actually gets bigger. What do I mean? As the radius of your kingdom, let's imagine it's just an expanding circle. As the radius increases, the amount of land you have is growing quadratically, right? It's going up with the radius squared. And so you do have issues where your communication distance that you can communicate effectively is within a certain radius, and so you've got interesting issues with the communication and how things work as it grows. But software has this similar problem, which is as you write lines of code, the complexity grows more than quadratically, right? And so you need a lot of structure and a lot of help to get it to go bigger. So where are those sources of complexity? I talk about this in much more depth in another episode. If you want to look at the sources of software complexity, search for that on my site on lispcast.com. But I'll go over two of them right now briefly. All right. So here's, and more, probably more directly. Here's the thing. Every conditional at least doubles the number of code paths. So every time you add an if statement, there's at least two branches. There's the else, the then and the else. Even if you don't have the else, the do nothing, it's like a do nothing branch, right? But it doubles the number of code paths. That means that potentially something will be different in each of those code paths. Yeah, it's more to test. It's more stuff that can go wrong. It's more you have to think about and analyze to know that, yes, that code path is possible and it doesn't break anything, right? It does give the right answer, right? So it doubles. So if you look at a typical program, typical piece of software, like it must have millions of code paths in it. Millions, trillions. And so you don't even notice, like, oh, if I just remove one if statement, let's say you're refactoring and you remove an if statement, you've halved the complexity. But it's so high already, you don't even feel it. It's already too complex to comprehend. Even though you've cut it in half, you've made a significant change. So it's really interesting that we get to this point where, like, it doesn't even matter if we add one, remove one. We don't feel the difference. It's just all. It's like if you're you have $10 billion and you like double your money, like, I don't care anymore. I can't spend it all. I can't even comprehend all that money. Or if you lose half of it, you're like, I'm still super rich. Which is really interesting. I think that we're at that point in our software that we just we can't intuit, we can't have this good idea of what our complexity actually is. And functional programming has some ways of managing this. The main way is that through data modeling, we can reduce the number of conditionals down to the sort of essential, right? I mean, you're going to need conditionals in your software because you're modeling some complex system that operates with the world. It needs a certain amount of complexity to it. But often we add conditionals, we add problems, more complexity than we need. And with good data modeling, in theory, you can reduce that number down to the essential bit. Okay. And right, I have an episode on this if you want to go deeper into that. I go into like the math of it and stuff. Okay, so the other source of complexity is something that we're dealing with more and more these days. Probably for the last 20 years, it's been pretty apparent that every action in sequence, when you're doing programming in parallel or in a distributed system increases the complexity. And it increases it in a combinatorial way. Because your operations, if let's say they're running on different CPUs in your machine, different cores, these are operations, these are operations, and on a different CPU. They can interleave in different ways every time they run. So you need to make sure that every possible way that they can interleave is a valid way, because you can't control it. You can't control the scheduler and how the CPUs are running and what they're doing at what time, unless you coordinate between them. Okay. But in general, the baseline is you can't control how they interleave. So you need to make sure that every possible interleaving gives you the right answer. And the number of possible interleavings has a factorial in it. So it grows really fast. So just as the way I like to show how bad it is if you have 12 operations in sequence on two different threads, 12 operations, 2 different threads, you're already at over 1 million interleavings. Do they all do the right thing? That's your job as the engineer, is to make sure that they either do the right thing or they can't happen. So functional programming doesn't have, I think, all the answers to this, but it has some answers, and it's asking these questions, right? It's been coming up with ways of limiting the number of interleavings. It's been coming up with ways of making it so that the interleavings don't matter so much, right? If you've got all immutable data, it doesn't matter, because if all you're doing is reading immutable data, even if it's shared, it's okay. Functional programming has been working on stuff with distributed systems. So even if you've got a single threaded system like you do in JavaScript, once you make a call to the server, you're now a distributed system, and you've got the same problems. Stuff happening on the server is interleaved with stuff that's happening in the browser, and the messages going back and forth are being interleaved. Like, it's just, you've got the same problem. And so I've said this before, I'll say it again. I don't think that functional programming is gaining popularity because of the cores that we've got, and we're trying to, make all this parallel software. It's not happening, not as much as we thought it would. Of course, in some places it is happening, but it doesn't seem to be like, oh, it's so necessary to make everything parallel all the time. But what is necessary is we're making web apps. We're making distributed apps. We're making an app on your phone that's talking to a server. Now you need to horizontally scale out your service, but you need to have some kind of consistency between the different servers. So now it's all distributed systems. And that's where functional programming is really showing its value, right? It's because we've been thinking about these problems for a long time. We have some answers. And so what do you do? Like I was saying, you can reduce the complexity that's inherent in this distributed system, in this parallel system. You can reduce it by limiting the number of interleavings, by eliminating certain possible interleavings from possibility, by limiting the number of things in sequence. Right? The longer your sequence is, the more interleavings there are by a combinatorial factor. So if you shorten your sequence, you actually have fewer interleavings, which is another way of doing it. So that means like doing less stuff with actions, with side effects, doing more stuff with calculations that don't lengthen your timeline. So that's why I talk about complexity. Functional programming, like I said, it doesn't have all the answers, but I think it does let you get, it lets you get to a bigger scale before you have problems, because you are going to still hit complexity limits. But it's also been thinking about the problems and has solutions where other paradigms don't. The solutions are like baked into the paradigm. This first notion of, is it an action, a calculation, or a data, already divides the problem up into the hard parts, the actions, the necessary but medium difficulty stuff, the calculations, and then the data, which is kind of the easiest part. Once you have immutable data, it's pretty settled. It doesn't cause problems. And then the data modeling is actually not so easy, right? It requires a lot of experience and design skills to model a problem as data. But that actually helps reduce the complexity. And just dividing things into those three things really helps clarify, where's my complexity, what can I do to reduce it to a minimum. And so I believe that the paradigm itself has baked in a lot of those, a lot of the solutions to eliminate complexity. Awesome. I'll just recap real quick. So complexity is the reason software gets harder to write as it gets bigger. I don't know why, but you see every piece of software like has this huge blossoming and blooming at first, all these new features, all this stuff, and then it kind of slows down. And it's not that people run out of ideas for features to add, it's just that they can't add more features without breaking existing stuff. It's too hard. It just gets harder. Every conditional doubles the number of code paths, and every action and sequence, when you're talking about parallel or distributed systems, increases the number of interleavings. And what we're really talking about is same with code paths and with interleavings. What will happen next? What is the next thing that will happen? And is that going to give us the right answer? That's always the hard part, because we have to reason it out in our heads. We have to play it out. What's going to happen next? And if there's 12 things in sequence and there's a million possible things that could happen next, it's no good, right? It's just too much to keep in your head. The same with the number of code paths. I've got all these branches. I don't know what's happening next. I don't even know what just executed. Right, so FP doesn't have the answers. It can't reduce this to nothing, but it does have frameworks for thinking about it. It does have a nice set of concepts that map nicely to these notions of complexity, to these sources of complexity. Pull out the things that are more complex, deal with them specially. You got calculations that are much easier to deal with because they don't add to the number of interleavings, right? And they're going to have conditionals, but with good data modeling, you can limit it down to the bare minimum. All right, thank you so much. You can find this and all the other ones, the past, present, future episodes from the beginning of time to the end of time on lispcast.com/podcast. I've got video, audio, and text transcripts of all of the episodes, depending on your mood and your predilection for different media. If you like the text, you like reading, go for it. If you like to listen in the car, you can subscribe. There's links to subscribe, and there's also links to social media, including email, Twitter, LinkedIn. However you want to get in touch with me, I am happy to answer questions. I love getting questions and talking about them in the podcast. Tell me that you appreciate me. Make me feel good. All right, people. Thank you so much, and rock on.